Have you ever wondered if we could get high-speed internet at the bottom of the ocean? Well, today we are diving deep, and I mean that literally, into some mind-blowing research that's trying to make that happen by solving a massive technological puzzle.
I mean, really think about it for a second. The radio waves that power our Wi-Fi, our cell phones, they just die in water. They get absorbed almost instantly. So if you want to send a lot of data fast through the deep, you've got a huge problem. But what if the answer wasn't radio at all, but light?
Exactly. A laser beam, a super-focused, high-speed pipeline for data. But, this just swaps one problem for another one. How on earth do you keep a tiny little laser beam perfectly aimed at a tiny little target when everything is moving and the water itself is trying to scramble the signal?
Okay, so here is the heart of the challenge. I want you to picture this. You're on a boat, it's rocking back and forth, and you're trying to shine a laser pointer at a tiny sensor on another rocking boat, maybe hundreds of feet away. Oh, and you're doing it through a swirling, messy, turbulent medium. That's the exact problem we're trying to solve here.
It really just boils down to two huge differences. Here on land, we have nice, clear, stable air, and things generally stay put. But underwater, it's a whole different ballgame. You're fighting against turbulent, shifting water and the fact that your transmitter and your receiver are probably moving. It's a double whammy, a chaotic channel, and constant misalignment.
So to even begin to tackle this, the researchers had to get really clever, starting with the signal itself. Let's actually follow a single packet of data as it's created and prepped for its big watery journey.
It all starts out as your basic ones and zeros. First, software translates those bits into a very specific pattern. Then, a piece of hardware, a waveform generator, turns that digital pattern into a real-life electronic wave. And finally, that signal is used to flicker a laser on and off at an incredible speed. That's basically how your data becomes a beam of light.
And the signal they came up with is just brilliant. It's not just the data. It's sent in a little packet that has two other vital parts. First, there's some zero padding, which helps figure out how noisy the water is. And second, and this right here is the secret sauce, a pilot signal. It's just a simple, predictable square wave that acts like a homing beacon, giving the receiver something really easy to find and lock onto. So, our signal packet is ready to go. Now comes the hard part, the journey. To test everything, the researchers had to perfectly recreate those messy, real-world underwater conditions right there in the lab.
They started with this, a 1.5-meter-long tank of regular tap water. It's like a mini ocean. And to mimic the temperature shifts that cause all that turbulence out in the real world, they just put a heating element at the bottom. This creates the exact kind of watery distortion the laser beam is going to have to punch through.
But remember, the turbulence is only half the problem, right? You also have to deal with the sender and the receiver moving all over the place. So the researchers added a very intentional wobble to the system. They did this with something called a fast steering mirror. Now, this is not your bathroom mirror. It's a high-tech, programmable device that can be tilted with insane precision. For this experiment, they programmed it to move in a specific pattern, deliberately knocking the laser beam off course. It perfectly simulates the kind of motion you'd get from a drone or a buoy bobbing on the waves. And listen, this is not some tiny little jiggle. The system was tested against a maximum misalignment of 9.3 centimeters. That means the laser spot could get knocked almost 10 centimeters off center, and the receiver still had to find it and track it. That just shows you how incredibly difficult this problem really is.
So, the big question is, how do you catch a laser beam that refuses to sit still? Well, the answer is just incredible. You don't try to hold the receiver still. You build a receiver that actually moves with the beam.
This is the big aha moment. The receiver board is designed with outer detectors that just look for the edges of the laser beam. So when the beam starts to drift off center, these detectors pick it up. A system instantly calculates where the center of the beam ought to be, and these powerful little motors physically move the entire board to line it up again. It's just like a baseball catcher seeing the ball is coming in a little wide and shifting their mitt to catch it perfectly.
This quote from the research paper says it all. The system adjusts based on the PD signal. That's the signal coming from those outer photodetectors. It's not a passive system at all. It's active, it's dynamic, and it's constantly sensing and reacting in real time to keep that connection absolutely locked in. Okay, so the beam is caught, the connection is stable, but the job's not over. How do we actually know that the message got through correctly? In any kind of data transmission, the ultimate question is always, how do you measure success?
The gold standard measurement is called the bit error rate, or BER for short. You can think of it like the final score for the transmission. It literally counts how many of the ones and zeros got flipped or corrupted along the way. The lower the score, the clearer and more reliable your connection is.
And to make absolutely sure their results were rock solid, the researchers didn't just run this test once or twice. They ran the entire transmission, sending 2.5 million bits through that turbulent, wobbly channel 1,000 separate times. That's how you get a really solid average for the bit error rate. That is scientific rigor.
The signal that makes it through is captured by an oscilloscope, and then it's fed back into the very same software where it all started. And here, the received data is compared to the original bit by painstaking bit to calculate that final error rate. It's the perfect way to close the loop on our data packet's incredible journey.
So, that's the experiment. Super cool lab setup, right? But so what? Why does any of this actually matter in the real world? Let's talk about the big picture impact.
Honestly, this kind of tech could be a total game changer. Imagine autonomous underwater vehicles, AUVs, that can send back crystal clear high-definition video in real time. Think about secure high-speed communication links for naval submarines that are nearly impossible to intercept. Or the ability to monitor underwater pipelines, cables, or even fragile coral reefs with a constant stream of high-quality data. This is how we unlock the digital potential of our oceans.
Which really brings us to the final thought. Something like 80% of our ocean is still unmapped, unobserved, and unexplored. This research is a huge step toward changing that. So I'll just leave you with this question. What could we discover if we finally had a high-speed internet connection at the bottom of the ocean?